this. So take any alpha between 0 and 1, and the power alpha of each Jordan block. And here we really use these properties because we have a function which has a branch cut on minus infinity 0, and it is only continuous at z equals 0. So if we had like 2 by 2 Jordan blocks, we would require derivatives in 0, and we do not have those. But fortunately, we have the properties that we require to define. So just for reference, this is how you define the alpha power of a Jordan block. So if you have a k by k block, you need the derivatives of the function up to order k minus 1. So just for reference. Right. So now that we have the fractional Laplacian, we can define fractional diffusion on a network, or you can say also fractional heat equation, let's say. So this is the differential equation that we have. So basically, it's the same as the diffusion equation, only that you have L to the alpha instead of L here. And you start from a probability vector u0, so vector with the entries that sum up to 1, non-negative vector. And you can also write the solution explicitly like this. So this is a matrix function times. Notice that here we are using row vectors. And the reason is because if we do this, then we have probability vectors for all times, which is what we want. And then later, when we compute this, we will just transpose everything. So here we will have a function of L transpose. Anyway, so let me just say a couple of words about the properties of these dynamics. So diffusion on a network can be thought as a discrete equivalent of a diffusion on N or something. So the Laplacian can be seen as the analog of the continuous Laplace operator. And similarly, you have that fractional diffusion on a network has non-local properties like fractional diffusion using the standard Laplace operator. So you can have the super diffusion properties and faster exploration of the network if you use, for instance, a random walk to explore the network. And now this was more just to give a bit of a context. And what we will need is that we have this expression that we want to compute. And the function here is a function exponential of minus tz to the alpha, which has a branch cut on this set here. And this will be the main issue that we will have to deal with in the solution. So now let's move on to rational proof methods. These are in general methods that can be used to compute expressions of this form. So matrix function times a vector without computing the whole matrix function, which is usually both expensive in terms of storage and the computational cost. So the idea is to use a small search space, let's say pk, which we constructed in a proper way using the matrix and the vector, and use an orthonormal basis of this space to extract an approximation of this vector. So say that we have such base, let's call it pk. The idea is to project the problem on the smaller subspace. So you take this matrix bk transpose abk, which is the projected matrix on the subspace. You apply the function to this matrix, and this is quite cheap because you only have a k by k matrix. You project the vector, and then you go back to the original space. So this gives you an approximation that depends how good this approximation is depends on how good the space is. So later I will show you a few examples of these spaces. And well, you can compute the basis using a rational only algorithm, but I will not go into too many details about this. So some examples of proof of subspace methods. If you use matrix vector multiplications to construct it, you can get a polynomial proof method. So you take b, a times b, and so on up to a certain power. So you get all the polynomials up to a certain degree, time of the matrix A times vector b. More in general, you have a rational proof method, which is defined using a certain sequence of poles. And then at each iteration, you have to solve a shifted linear system with the matrix A with a different shift in general. So you would build it this way. So this is basically rational functions in any up to a certain degree with fixed denominator. And finally, this is a special case of the rational proof method where you have all the poles equal to the same pole, which is called the shift and invert proof method. And basically, what you do is that you have a polynomial proof subspace with a shifted and inverted image. So hence the name shift and invert. And this is easier to compute because maybe you can, if you use direct methods for the solution of linear systems, we can say factorize the matrix once and then reuse the same factorization for all the solutions. Okay, so this was a brief overview. Now let's move on to the main part of the talk, so the singularization. So the problem in our setting is that when you look at convergence results for field methods, you see that these results usually require you to have the spectrum of the matrix and then a region of analyticity of the function around this spectrum. And the larger this region is, the faster you can expect to have convergence, both theoretically and in practice. And in our situation, we have a bit of a problem because we have a branch cut on -infinity 0, as I showed you earlier. And we also have 0, which is an eigenvalue of the graph function. So we have an eigenvalue exactly on the border of the region of analyticity. So how can we solve this problem? So I again repeat that this is not only a theoretical issue, but it can also give you problems for the actual convergence rate of the methods. And an idea is to somehow remove the 0 eigenvalue of the graph function with a certain the singularization, which I will show you in a few moments. And the idea is, so if we remove this eigenvalue, we can expect to have faster convergence, and so this will be actually useful in practice. So let's focus on the case where we have a strongly connected graph. So we have only a simple 0 eigenvalue. And so in this case, we know that the right vector is the vector of all ones, which we will denote like this. And in general, we have a left eigenvector, which we know it is positive, and we can also normalize it so that we have this product equal to 1. And in particular, if we have an undirected graph, we can choose it without, in general, we would have to solve this linear system. And for an undirected graph, we can just choose it again as a multiple of the vector of all ones, since we know that the matrix is symmetric. So these will be the three methods that I will show you for the singularization. So one is a rank 1 shift, one is a projection on a subspace, and one is basically an implicit projection that doesn't change the Laplacian and only works on the initial vector. So these are all things that basically make the matrix non-singular. So they remove the 0 eigenvalue. So the rank 1 shift is quite straightforward. You just take this shift here, 1 z transpose, which is a rank 1 shift that moves the 0 eigenvalue to a 1 eigenvalue, since these are eigenvectors of the matrix. So this shifted matrix is just a matrix with the same eigenvalues and eigenvectors, except for 0, which is moved to 1. And so it's easy to see that you have this identity. So if you want to compute a matrix function using L, you can do the same using the shifted matrix. And then you just have a rank 1 correction to account for this change of 1 eigenvalue. And so if you want to multiply this by a vector, you get this easy relation. And so if you want to use, say, a rational field method to approximate this quantity, you can just approximate this other quantity with the rank 1 shift, and then use a simple correction to get back what we originally wanted. And so this can be done without too many additional computations, since we can recover the original thing for just order n cost. And these linear, say, if you use a rational field method here, you would need to solve linear system with this matrix, and you can do this with the Sherman-Morrison formula by using, again, the original matrix. So you don't have to build this matrix explicitly, which would, this is no longer a sparse matrix if you have a sparse Laplacian. So that would be expensive to store and also to solve linear systems with it. So you don't have to do it explicitly. And for the projection, we project on the subspace, which is orthogonal to the vector of once again. And by doing this, if you have, say, an orthonormal basis of this space, you get an n by 1, n minus 1 by n minus 1 matrix, which is non-singular. And you can see that if you start from a vector which is orthogonal to the vector of all ones, if you try to compute this quantity, it is the same as computing it on the projected matrix. So if you take in general any vector, you know that you can write it as a multiple of z in order to account for the component along the vector of all ones, plus something which is orthogonal to the vector of all ones. And if you want to compute or approximate this quantity, you get this relationship by using that this is equal to this. And so again, you can, if you want to use, say, a rational proof method, instead of using it on the original matrix and the original vector, you can do it on the projected problem here. And I will not go into details about this, but again, you don't have to explicitly compute this matrix. You can find a Q which only requires order and operations to do matrix vector products, and you can go from solving linear systems with this shifted linear systems with this matrix again to solving shifted linear systems with the original matrix. I can give you more details later if you want. Okay, so now for the final thing, which is the implicit projection. So the main observation here is that for orthogonal vectors orthogonal to the vector ones, you have this identity. So this identity tells you that if you want to approximate this, you can use either a rational proof method on the left side, so you would use L transpose and U as matrix and vector respectively, or you can do it on the other side. So say that you do this. So we have a vector orthogonal to the vector all ones, and you approximate the left side of that equality using k steps of a certain rational proof methods with whatever poles you want. And then you can also do the same on the other side using the same poles. So you approximate this using the projected matrix and projected vector. And it turns out that you're actually computing exactly the same approximation at each step. So this means that if you want to do this projection approach, you don't have to project explicitly. You can just use this expression below, which is just the same as this one without the projection. And you can expect to have the same improved convergence that you would get by using the rational method on the projected problem. So this might seem strange. You might think that, well, so I would get the same convergence as if I would approximate on the vector B. But it turns out this actually gives you an improvement. I will show you the experiment later. Okay, so this was it for the theory. So let me say the experiments were made using various graphs, both directed and undirected, with about 10,000 nodes. The expression that we computed is this one. So you have different values of alpha, different values of t, and a random initial probability vector. So the preload methods that we used are the polynomial method, so all poles equal to infinity, two different variants of the shift and revert method. So one with a repeated pole, which is computed using the extreme eigenvalues of the Laplacian, and the other one is one which was proposed in this paper by Moretti and Novati, specifically for functions with fractional powers. So you see that here you have the parameters t and alpha from the function. And finally, another method based on distributed sequences, which produces asymptotically optimal poles, specifically for Laplace-Stieltjes and Cauchy-Stieltjes functions, which was proposed in this paper by Massey and Rogel, and you will hear about it later by Stefan. Right, so this was the introduction for the experiments. So let me just describe here the legend. So you have above each graph, you have name of the graph and the parameters. So here you have 4 different colors. I hope you can see them well. And the color tells you the method, so polynomial, 2 different shift and revert, and the asymptotically optimal one. And the style of the line tells you what the singularization was used. So full line is no desingularization, and the other ones are shift, projection, and implicit projection. Implicit projection is the one where you just move the initial line. So it's interesting to see that you get basically the same convergence for all the singularized methods. So it's the same what approach you use, they all give the same benefit. And well, in general, you can see that polynomial methods, which is the line above, is quite slow, as we can expect, since you have a non-analytic function. The one with the asymptotically optimal poles is the fastest. And in general, you see that the singularization can give you about 2 orders of magnitude of increased precision. And you can also get a higher final accuracy. So here you could get, say, 10 to the minus 15 almost, and otherwise you could get 10 to the minus 13, 10 to the minus 12. Well, another thing to note is that the Moretti-Novati choice gives you convergence that is almost the same as the EDS one when you have a large time. Otherwise, you can have slower convergence, so that's good, specifically for large times. Oh yeah, I didn't say these were all undirected graphs. Here are the experiments for directed graphs, and you can observe basically the same thing. So the EDS method is always fast. Moretti-Novati method is good for large time, like in the first plot. And yeah, you can also have good convergence for the polynomial method. This matrix is quite well conditioned. You have a small spectrum, so you can get fast convergence here, but otherwise, in general, you can also get very bad convergence. So it's advised to use rational method here. And again, you see that the singularization gives you like 2 orders of magnitude of both increased convergence speed and increased final accuracy. Right, just to sum up, so rational methods are in general more effective than polynomial ones when you use non-analytic functions. This is well known. So the desingularization strategies that we proposed are similar in terms of performance. They all give you faster convergence and higher accuracy. Sometimes they don't, but they certainly do not hurt when you use them. And if you want to use desingularization, you only need one left-angled vector of the graph of Laplacian with 0 eigenvalues. So you just have to solve one additional linear system. And this is not a big deal if you're using rational methods, since you solve a linear system at each iteration. And finally, you only need order n cost per iteration in addition. And the cheapest method is the one with the implicit desingularization, which only requires changing the initial vector and updating the solution at each step. So the actual Krylov method is the same. You just use a different initial vector. So here are the references. So the second paper is the one where you find most of what I said, and also more details. These 2 papers, so the third and fourth one, are for the poles that we used. And if you want to know more about fractional dynamics on networks in general, you can look at the first one or the last paper. Right, that's all. Thanks for the attention, and I'd be happy to take your questions.
Thanks for being here. Thanks for this very nice talk. Are there questions or remarks? Yes,
I was wondering about the implicit singularization you were talking about. So you start from a vector which is orthogonal to the vector of all ones. Is this something that you need to make sure stays true throughout iterations, like by reorthogonalizing, or it doesn't matter much?
So it kind of happens automatically, since you. So it turns out that if you start from a vector which is orthogonal to the vector of ones, so you just change the initial vector, right? B has a scalar product 1 with the vector of ones. You will have scalar product 0, and it turns out that you don't need to do anything. It happens automatically. Otherwise, if you don't do this, so if you don't do any desingularization, it turns out that you don't get always scalar product equal to 1. And I didn't say it, but if these plots for the first, say for the full lines, they all require you to make sure that you have scalar product equal to 1 with the vector of all ones. So the singularization also gives you this property. It's not proved, I mean, but in practice, it turns out that you don't need to do anything to keep the orthogonal, the fact that the vector is orthogonal to the vector. So this is all basically the fact that you are, all the contribution is here. So here is where you.
Yeah, I was also wondering about roundel patterns or this kind of thing, if they can break this property.
Apparently, they don't break it if you use desingularization. They break it if you don't use it. So just to show you, if you don't use desingularization and you don't do anything, you get like this convergence, which is very bad, right? So otherwise, if you do a certain correction or desingularization, you get this nice line.
Okay, thank you.
different from chart or online? So if not, let's thank Igor again. Now it's time for presenting Fabio's studies. From the University of Pisa. No. He will present mixed-layer functions and their applications in network science. Please, Fabio.
Thank you, Maria, also for the introduction. And as you said, I'm going to talk about the application of mixed-layer function in network science. And this is a joint work with Francesca Rigo from Strathclyde University. So from the top, even if Igor has already given the basic definition, so I'll try to go fast on this. So what is a complex network? Well, a complex network is in a way just a graph in which there are non-trivial topological features. So this means that I want to use real-life graphs, so non-structured graph like lattices or Kelly graph. And I want also to avoid completely random graphs. And what information do I want to harvest from the network may differ. So, for example, one of the problems that usually one wants to solve is recognizing groups into the network. So finding clustering, so groups of nodes that behave in the same way, or maybe rank the nodes following a concept of importance. So we may want to discover what are the most important nodes in the network. Or maybe we want to discover what are the most important edges in the network. And there are many other tasks in exploratory data analysis that could be, for example, in locating motifs in the network, computing fluxes and stuff like that. But for what I'm going to talk about today, I will focus on network centrality for nodes. So the standard definition is, for us, the network will be a graph, so a couple of sets, a set of nodes and a set of edges between them. We could have directed edges, so they are in which the order matters, and directed edges, or loops, so a node that is connected with itself. And for everything I'm going to talk about, we will not have loops anywhere. Then to work with this object, we need to represent them in a way that is amenable for doing computation, and this way is transforming them into their adjacency matrix. So since this is the example, the adjacency matrix puts in position ij the weight of the edge, and if the edge is unweighted, this is just 1. So in general, if as in this case, as in this example, the network is undirected of the node, the resulting matrix is not symmetric. So what are degree centrality? As I was hinting before, we want to find what are the most important nodes in the network. So we want to rank them somehow. And two extreme cases that we can think about are, for example, degree centrality. So we count the number of incoming or outgoing links from every node, and this gives us a ranking. What's the problem with this one? Well, the problem with this one is that it is oblivious of the whole topology. So we have got only a very local information. We can look instead at an eigenvector centrality, so we can exploit the algebraic properties of the matrix A to get as a measure the Perron eigenvector, the entries of the Perron eigenvector for A, and this is somewhat better because considers both the number of neighbors and their importance when assigning the score. And these two types will be important as a comparison in the from what I'm going to talk about next. Another way of finding what are the important nodes in the network is to use the walk-based centralities. So this means that we take a function that admits a series expansion and consider this matrix function here. So what's the idea? The idea is that we are weighting the length of the walls on the network with decaying weight. So shorter walls are more important, walk of length 2 are less important, and so on. And this can be used to build the measure we are interested in. And what are the two most popular matrix functions for doing this? Well, the exponential and the resolvent. And how do we build the measures? Then, given the matrix function, we take the II entries, so this gives us the value of the centrality of the node, or we compute the total communicability, so we sum up all the values on a row, so this means that we do the f of a times the vector of all ones and take the height entry. So, okay. And as you see, if you change the measures, the value given to the nodes actually changes, but what we are actually interested in is not really the value, but the ranking. So I will always be looking at the ranking even if and not at the actual value. So where does the Mittag-Leffler function enters the fold? Well, they enter it because in a way, Mittag-Leffler function interpolates between these two behaviors. So you can choose parameters for it to have either the resolvent or the exponential or some other closed form. There is a plethora of this possible relationship. And the idea behind what I want to do is, let's say, okay, I know how the measures behave for this one. I know how the measures behave for this one. Let's see if we can find something in between the two that captures